Hello, I'm Álvaro Calafell, and this is the third part about the impact of harmonics in electrical installations. This part presents the impact of harmonics on power and neutral conductors. The main effect on power conductors is the increase in Joule losses due to the increase of the conductor effective resistance and the increase of the root mean square value of the current through the conductor. Such increase produces the power conductor derating. The increase of conductor effective resistance is due to the skin and proximity effects. The skin effect is the tending of the high-frequency currents to become distributed in the surface of the conductor, which increases the apparent resistance. The proximity effect results in the increment of the apparent resistance of conductors due to the presence of other neighboring conductors carrying current. When conductors carry currents of high frequencies, they are not uniformly distributed on the cross-section area of the conductors, increasing its apparent or effective resistance. The increase of the root mean square value of the current flowing through the power conductors is produced by the presence of harmonic currents consumed by nonlinear loads. As an example, given a current with a harmonic spectrum as shown in the plot, the root mean square value of the current flowing through the power conductor is increased 1.5 times the fundamental current. This increase produces the derating of the power conductor, whose cross-section may be oversized in the presence of these nonlinear loads. The main effects on neutral conductors are the increase of the Joule losses, which cause the neutral conductor derating, and the presence of high voltage drops. Considering the current in direct, inverse, and unpopular sequence, the current flowing through the neutral conductor in a three-phase system with linear loads is equal to 0, because the sum of the fundamental currents in the neutral conductor is null. However, the neutral conductor is not zero when nonlinear loads are connected in the three-phase system. This is due to the triple harmonics flow through the neutral conductor. The other harmonics are null because their three-phase currents are shifted 120 degrees in direct and inverse sequence, but the triple harmonics are in phase, and therefore their arithmetical sum is 3 times the current in the power conductor. As an example, given a current in the power conductor with the harmonic spectrum in the plot, the root mean square value of the neutral conductor current increases 2.6 times the fundamental current. This increase may burn the neutral conductor if it is not designed with the correct cross-section. This cross-section is small if the supplied loads are linear because the root mean square value of the neutral conductor current is null, but it must be the same or greater than the cross-section of the power conductor if the supplied loads are nonlinear in order to drain the triple harmonic currents. Hello, I'm Álvaro Calafell, and this is the fourth part about the impact of harmonics in electrical installations. This part presents the impact of harmonics on measurements. We have just talked about the impact of harmonics in conductors, and now the presentation will be extended to measurements in harmonic presence. Harmonics can produce erroneous measurements of voltage and current root mean square values. Imagine that we have an electrical circuit supplying nonlinear loads with a sinusoidal voltage in the plot. The current consumed by the nonlinear loads is a non-sinusoidal current in the figure, which corresponds to the typical one-peak waveform of the current consumed by single-phase rectifiers. There are different types of ampermeters and voltmeters to measure this current and voltage. The moving iron measurement device provides the true root mean square values for all kinds of periodic waveforms, so the measurement of the root mean square value of voltage and current will be correct. The ampermeters and voltmeters sensitive to the peak values of the waveform measure these peak values and multiply it by the factor shown below to obtain the root mean square value of the voltage and the current. The ampermeters and voltmeters sensitive to the average value of the rectifier waveforms rectify the waveforms, measure the DC value of these rectified waveforms, and multiply by the factor below the DC value in order to obtain the root mean square value of the voltage and the current. Both factors are the ratios between the peak value of the DC value of the rectified waveforms with the root mean square value in sinusoidal waveforms. This means that the measurements of the root mean square value of sinusoidal waveforms, such as voltage, will be correct, but this is not true for the non-sinusoidal waveform such as the current in the plot, because the previous factors will be different. In the example shown below, we can see the error found in the current root mean square values when measured with ampermeters sensitive to the peak value or the TC value from the rectifier waveforms. We have represented the currents from discharge lamps with magnetic ballasts, single-phase rectifiers, compact fluorescent lamps, LED lamps, three-phase rectifiers, and 6-fold rectifiers. We can observe that the more the current differs from a sinusoidal waveform, the greater the error of the root mean square value. For example, a single-phase rectifier or compact fluorescent lamps. Harmonics can also produce errors in the measurements of the active power. According to the video on active power, the expression which includes harmonics is the following. The inductive and electronic equipment do not correctly measure the active power because they introduce different approximations in the measurement. The inductive equipment does not consider the distortion factor in the determination of the active power. The electronic equipment determines the active power from the root mean square value of the voltage and currents derived from the peak value of the waveforms and the mean value of the rectified waveforms.